Hi, Dr. Sherry. So, today for the lab, we did resistors in series and parallel. And so basically, I went through and did like the initial setup where I took, what I took. Okay, so I did the wire and I connected the ammeter, the resistance, and I did a second wire and I made a closed loop. And from that, I got the non-zero reading of 0.90. And then once I double clicked the resistor and changed it to 100, I saw that it was a decrease in a potential difference where it went to 0.09. So it had a voltage drop across the resistor, which was what was expected. And so then I dragged the voltmeter to both of the opposite sides of the resistor. And then I had, for the current, I had got 0.09, and for the voltage, I had got 9. And so then from there, the resistors connected in series. And so I had a resistor that was 100 ohms, and then I had a second resistor that was 50 ohms, and I basically did it to look like the picture. And so when I did it, I looked at the potential difference across the battery first, which was 9. Then I looked at it across the first resistor, which was down here, and I had got 6. And then for my first resistor, that was the one that was 100 ohms, and that was the one that was 6. And then for the other one, I did it when where it was 50 ohms for the second resistor, and I got 3. And so then I had all my 3 ammeters, which was all in these locations, and those were the same. I had got 0.06. So it asked, was there any difference between these currents? And of course there was no difference between the currents since all the values were the same. And so basically the current that was going through R1 was the same current that was going through R2 because they were both 0.06. And so from that, I had developed a relationship. So for IT, I saw that it equals to I1, which equals to I2, which was 0.06. And then for the voltage, I saw that that the delta VT is equal to delta V1 plus delta V2, because I had got 9 for the battery, and then I got 6 for the first potential difference across R1, and 3 for the second potential difference across R2. So 6 plus 3 equals 9, and so that was basically the relationship. And from that, then derived an equation in order to get R like as a whole. And so from what I said before, I took the delta VT is equal to delta V1 plus delta V2, and then Ohm law's equation is V equals IR. So from that, we know that delta VT is equal to delta V1 plus delta V2, which is equal to, from the Ohm's equation, I times R1 plus I times R2, basically, because that is what V equals. And then if we was to take that, so you don't have to do it twice. If we was to take it and condense that, it would be I in parentheses, then R1 plus R2, and that would give us IR as a whole. And so I used that equation. So for my values, I got 0.06, and in the parentheses, I had the 100 ohm plus 50 ohms, and so got 90 ohms as a whole. And so yeah, that was my resistance as a whole. And then for resistors connected in parallel, so basically I had to rearrange it and do it like this. And so for this one, this was a basically kind of like the opposite of what it was in a series. So as far as the voltages, I got the same thing instead of the currents being the same thing. So for all my voltages, it was 9. And so, and then it asks, was there any difference between the current leaving the battery on the positive side and also coming back into the battery on the negative side? And so, no, there was no difference between the current leaving the battery on the positive side and coming back to the battery on the negative side. Both of the values were 0.27. Which demonstrates that the same current that was flowing through, that the current was the same, that the current, I can't get my words out. I'm sorry, sure. So basically, this demonstrates that the current flowing through it is the same for this particular loop section. And when the wire was connected basically to one side of the battery, that it had the same current going in one side as it did coming out the other side. But that was specifically for the battery, but the currents that was going through the resistor were different, because the one that was going through the first resistor, which was the 10, I said the 10, the 100 ohms, was 0.09, and then the one that was going through, I'm just making sure, yeah, 100, and then the one that was going through the 50 was the one that was the 0.18, which I actually have shown it right here, even though I did include a picture like with the email when I send it. So basically it said to do the relationship that was derived from that. And so for this one, it was basically similar to the other one, but just opposite. So for IT, it was equal to I1 plus I2, because the one that was going through the battery was 0.27, and so then when you take the 0.09, the one that was potentially different that was going through the first resistor, and then plus the 0.18, which was the percentage difference that was going through the second resistor, then that's 0.27. And then for the voltage, they were all the same, so I did delta VT equals delta V1 equals delta V2, which was 0.09 volts. And so then from there, we develop our relationship. So we know that IT is equal to I1 plus I2. And then we take the Ohm's equation and we rearrange it. We know that V is, that I is equal to V over R. So we know that IT is equal to V, and then in parentheses, I over R1 plus I over R2, because, I mean, that's what it is for I. We're just doing it for each resistor, and so basically that's equal to V over 1 R the whole thing. So we know if we wanted to calculate the resistance for the whole, for like as sum wise for the whole thing, that we basically would do 1 over the RT equals 1 over R1 plus 1 over R2. And so that's what I did. So I did 1 over 100 ohms plus 1 over 50 ohms, where I got 0.03. And so then I took 1 over 0.03 to get the total resistance, which was 33.3 ohms. And so basically that was the lab. It was really pretty simple. It really wasn't that bad. And I got through it pretty like fairly quickly. So I mean, yeah, that's all. That was the entire lab. And I hope you liked the video, and you have a great day, Dr. Chivalry.